All right, so introducing the basics of integration here with a focus on using our GDC a lot. Later on, we'll take more of an algebraic approach. And in essence, when we see an integral of something, we can imagine it representing the area between a curve and the x-axis. So I'm going to look at this example right here. I'll look at this function here, and I want to think about the area of this function bounded between x equals -8 and x equals 4. So for a visual of this, I'm going to go to Desmos. And this is what it's kind of visualizing. If I zoom out, what you see in dark blue, that's the graph of the x squared plus 17x plus 106 over 2 times x plus 11. That's the rational function. However, we want to look at just the area bounded between that, the x-axis, as well as these vertical lines of x at -8 and x equals 4. And that's what you see, those vertical lines. And so this area we see shaded, that can be represented as an integral. And so maybe first kind of represent this, how we formally write what I'm describing here. And so this here we can say is the integral. Oh, that's a highlighter. We want the integral from -8 up to 4 of the function x squared plus 17x plus 106 all over 2 times x plus 11 times dx. Now, keep in mind, a little bit here, this here is clearly that function. The -8 and the 4, those are the bounds of the beginning and the ending of the shaded area. This dx, you can imagine it as representing the width of a rectangle. And for example, we can imagine the idea of taking this function and finding the sum of all these infinitely narrow rectangles and adding them all up. Each rectangle has a height that matches the output of this function, and each little of these infinitely many rectangles has a width that is infinitely close to 0, this dx. That's it. In practice, that dx is an important idea, but it's not something you need to worry about too much as long as you just realize that it is relating to the variable we're integrating, in this case a variable x. And it has to do with, again, this idea that this is the sum of, if we want to find this area, of infinitely many incredibly skinny rectangles. And to find the area of each rectangle, it's length times width. And again, the width we are imagining being infinitely close to 0, the limit as we, approaching 0. With that said, though, you can just type this exactly as I have here into your GDC, and that is something you're expected to know how to do. And so if you type this into your GDC, you should get approximately 56.2 to 3 significant figures. You're also expected to be able to graph this in your GDC. And in general, you graph this function, and then depending on your GDC, you can get it to calculate the integral. And you should be able to quickly see something that is not quite as colorful as this, but it looks pretty much just like this. And so keep in mind, on your GDC, once you can graph this integral as well, it should also tell you the numerical approximation for the integral, about 56.2. All right. And so like I said, right now, our GDC is kind of pretty critical. It always will be very important in this course, but right now, we're going to rely on it a lot. All right, so next, similar idea. I want to use my GDC to evaluate this integral, both by graphing as well as directly evaluating an integral expression. So maybe I'll just mention the directly evaluating it. So again, this is the integral from point 0,1 to point 0,2. So a small little interval on x of this, again, this rational function. 1 over x squared plus x dx. Which, by the way, this times dx, another way of commonly writing it is almost identical. But instead of having essentially 1 times dx, I can just put a numerator of dx over x squared plus x. So instead of multiplying this fraction by dx, I can just say, well, it's the same as having just dx in the numerator. It's the same thing. I've noticed in IB, they don't tend to show it like that, but who cares? That's a very common way. That's it. You type this into your GDC, and you should get approximately 0.683 to 3 significant figures. that's it. With graphing, a little bit trickier. So I'm going to go back to Desmos here. And if I just graph this without thinking about my window settings at all, I don't really see much here. And that's because I'm only looking at the region from 0.01 to 0.02. So whenever we rely on a graph, as always, our window settings are crucial. And while you don't need to make 0.01 your X min and 0.02 your X max, you can pretty much do that. And so if I zoom out, if it lets me, here we go. I'm going to kind of stretch this and compress this down. And now this is the region this is much more easy for me to visualize. I've expanded my X scale a lot. So I've zoomed in a lot so that on my X scale, I can see that 0.01 and 0.02. I can now see this region much more sensibly. And again, that has an area of about 0.683. And so just anytime you're relying on graphing, those window settings are always crucial. All right, next time I give you the graph. Okay, and this is the graph. In red, we see of root x. So let me just kind of label that. This is the graph of y equals root x. And I have this shaded region. I want to define the shaded region with an integral and then evaluate it. Well, if I look at my graph, this is the region below root x and the x-axis between 0 and 4. And so I can express this as an integral from 0 to 4 of root x dx. And I can use, at that point, I can just type this into my GDC. It's probably fastest not to actually graph it, just to type it in directly. And you should get about 5.33. And keep in mind again, I want to just go back to this dx idea and root x. The idea is for this integral, this area, we're imagining this shape being broken up into infinitely many very, very narrow rectangles. Each of these rectangles has a height equal to root x, depending on the x value, and a width that is infinitely close to 0. That's the dx part. And so just like with slope and the derivatives, we have the derivative is dy over dx, where this is like our rise and our run, where we are making our, in this case, run, our horizontal change infinitely close to 0. But never actually at 0. All right, that's it. I'm done. So lastly, here I have a graph. This time it's showing me a velocity time graph with x in seconds and y in meters per second. So let me kind of label this here. So this is time in seconds, and this is velocity in meters per second. All right, I want to evaluate this integral from 0 to 7 of this. And then think about what it means. Well, this time I don't need a GDC for this. I can actually just find the area directly by breaking it up into a series of rectangles and triangles. So I have a square here, I have a rectangle below, and then a couple triangles. All right. So that said, each of these is quite easy to find the area of. This is an area of 5, area of 9. This triangle is base times height divided by 2. That is an area of 3, and this is an area of 4. And so altogether, add up all these, I get 21. So this equals 21. But 21 what? What does this mean? Well, notice, if I'm finding area, I'm essentially breaking this up into length times width or something like that. In this case, it's my x times y. So my units are meters per second times seconds. So it's 21 meters per second, that looks like a 5, meters per second times seconds. Well, notice I can see that these seconds cancel out. And so that gives me a sense about what this means. My answer is 21 meters, which means this integral here represents the total distance this object traveled in the first 7 seconds. Right, because it ended right here. So again, the total distance traveled in 0 to 7 seconds. It traveled 21 meters. And anytime we have an integral of a velocity time graph, it represents a distance traveled for this very reason right here, that we're multiplying velocity times time, the time cancels out, and so we end up with just the distance. These are ideas we will go much farther in detail, especially in HL, but good little introduction stuff. Finished.